The rising Chinese nuclear industry. Bismarck Brief, the 24th of May, 2023. China has built up its civil nuclear fleet from nothing to second worldwide. It is on track to become the world's largest producer of nuclear power, yet it won't lead a nuclear energy revolution. From 1992 to 2022, China went from having no civil nuclear fission power to being the second largest producer of nuclear energy, behind only the United States, having eclipsed France in 2020. While nuclear power has stagnated globally, Chinese civil nuclear infrastructure has grown to 55 completed nuclear reactors, with another 22 currently under construction. These have a total capacity of 53 gigawatts, with another 22 gigawatts under construction. They currently produce around 5% of China's total electricity generation. Total capacity is expected to reach 70 gigawatts by 2025 and 145 gigawatts by 2035. This would make China the largest producer of nuclear energy worldwide, exceeding the U.S. nuclear fleet's capacity of 93 gigawatts by the end of the decade. Thus far heavily reliant on Western expertise, the Chinese nuclear industry has been the primary outward opportunity for U.S. and European nuclear energy providers who are stagnating in their domestic markets. Some designs which have faltered in the developed world, like the European Pressurized Reactor (EPR), have been successfully constructed in China. China is projected to host between 40% to 60% of global nuclear capacity by 2050, and Chinese companies are beginning to compete in novel nuclear technologies like small modular reactors, SMRs. The export market for Chinese nuclear technology is less assured, due to both U.S.-led restrictions and fierce competition with Russia's state nuclear corporation Rosatom, so the primary consequences of China's nuclear expansion will be domestic. Even as China's industrial economy has grown to become the largest in the world in recent decades, China continues to get most of its energy from coal. As of 2021, coal provided 63% of China's electricity and 55% of overall energy consumption, which also includes heating and transportation. Coal's share has decreased markedly since the early 2000s, while every other energy source has grown. This is true for nuclear, but it is also true for other low-carbon sources, such as wind or solar photovoltaics. Usage of oil and natural gas has also grown, showing immediately minimizing carbon emissions isn't the primary goal. The Chinese government is an ideal patron of nuclear power because its energy demands are still growing quickly. It is concerned about energy security, and it wants to further develop the nuclear capabilities of its military forces. But while nuclear power is becoming more Chinese, it is not planned to become the primary energy source for China. Rather than embark on a program of energy abundance through nuclear power, Chinese planners envision the country becoming developed, based on U.S. and European energy use per capita, by 2035, and officially plan to reach net zero carbon emissions by 2050. Nuclear power is just one tool to reach this limited aim, along with renewable energy sources and natural gas. Growing energy consumption allows nuclear build-out. Between 1980 and 2021, China's total energy consumption grew from an estimated 4,828 terawatt-hours to 43,791 terawatt-hours, in order of magnitude increase. Electricity consumption per capita has also grown by an order of magnitude. For comparison, U.S. energy consumption per capita has flatlined since the early 2000s, and per capita has actually notably decreased. U.S. energy consumption per capita peaked in 1973, years before China even began its economic rise, and has since declined by about 22%. The vastly different trends in energy usage are a key factor in explaining the rise or stagnation of nuclear industries, since the fundamental appeal of nuclear power is abundant baseload electricity. In terms of installed electrical capacity, nuclear power isn't notable in China. The total installed electrical capacity in 2021 was 2,380 gigawatts. This puts the 53 gigawatts of nuclear power at about 2.2% of installed capacity. In reality, due to the higher capacity factor, the actual generation compared to the theoretical maximum of nuclear power relative to other energy sources, actual generation from nuclear power is closer to 5% of generation. By 2035, China is expected to have up to 5,000 gigawatts of installed electrical capacity. If nuclear power reaches 145 gigawatts by then, it will constitute 2.9% of installed capacity. Under scenarios by the China Nuclear Energy Association, nuclear installed capacity could be 328 gigawatts by 2050. In contrast, total capacity could be as much as 7,100 gigawatts, driven by the demands of electrification. Nuclear power would therefore represent 4.6% of total capacity by 2050. Nuclear power's contributions could exceed this by a factor of 2 or possibly 3, since solar and wind power capacity accounts for the majority of new additions to capacity, and their capacity factor is very low compared to nuclear. China's solar photovoltaic capacity factor was about 12% in 2023, compared to 20% for the US and 27% for Chile, the current world leader. Poor capacity factors are in large part a result of solar panels being deployed in developed zones with low solar irradiation instead of more remote high irradiation zones. In contrast, the capacity factor for China's nuclear fleet was generally over 80% and nearly 90% in recent years, higher than the world average. With similar assumptions, nuclear generation could account for between 10 to 15% of Chinese electricity by the middle of the century. This is a somewhat lower proportion of overall electricity generation than that achieved by the US and far lower than France, which still produces about 70% of electricity from nuclear power. While China's nuclear industry might become the largest in the world in terms of revenue and number of reactors, nuclear fission won't be the most important source of electricity for China. In the West, nuclear power was largely deprioritized or even phased out deliberately in favor of renewables, which have been marketed as technologies that could provide electricity as overall energy use stagnates. In contrast, China is developing the two categories at the same time, since renewables are seen as yet another energy source to feed rapid consumption growth. Chinese energy policy is enshrined in the Chinese Communist Party's 5-year plans, which guide national economic development and industrial policy. The 14th plan was outlined in 2021 and runs until the end of 2025. It differs from other 5-year plans by not setting a GDP target for the period. It also stipulated reducing carbon emissions and diversifying the economy towards services, with the intention of reaching peak carbon emissions before 2030. It set out the aim to reach net zero emissions by 2060. This 30-year window from peak emissions to net zero emissions is extremely ambitious, even set against the standards of Western countries. Long-term, China is expecting to stop its energy consumption growth by 2035 and become considerably less energy-intensive in relation to economic growth. On paper, China is therefore following the same trajectory as other developed countries so far, gradually substituting expansions in energy consumption with efficiency and greater diversification into less energy-intensive economic activities. The paradigm of becoming a developed nation, where industrial and economic growth eventually stagnates for the sake of efficiency, remains firmly intact, showing that China doesn't have any plan or theory of how to further develop their industrial society beyond imitating Western economies. There are major concerns for economic security, but there are no plans for energy abundance beyond what is already present in the US. Despite these stated ambitions, in 2022, the two sessions, an annual policy meeting between top officials, saw commitments to expanding the coal supply reprioritized on energy security grounds. Coal's share of electricity generation has decreased from 80% in 2007 to 62% in 2021. In 2022, coal use increased as a share of generation. Ultimately, coal is cheap and easy to obtain, with China having the fourth largest reserves worldwide and producing the vast majority of coal it consumes, with any shortfalls easily imported from coal exporters like Russia or Australia. As China has become older and wealthier, the increases in Chinese labor costs have made maintaining low energy costs more important for manufacturing competitiveness. As coal can be easily applied to industrial heat applications as well as electricity, it is critical to continue Chinese dominance in process industries like steel. While coal is projected to no longer be a majority of Chinese electricity generation, it will remain a significant source of energy and will see actual demand grow beyond the current level. This is not to the detriment of other fossil fuels, as natural gas demand is also projected to increase 50% from 2021 to 2030. This has allowed China to become the largest or second largest buyer of liquefied natural gas, LNG, on the global market. Chinese demand for electricity is strong enough that multiple players across different energy industries can make considerable investments simultaneously. Both nuclear and renewables lower pollution, create jobs, and reduce the need for imports, while having considerable export potential, assuming control of the renewable supply chain, which China has. The majority of solar power supplied to Europe and the US is dependent on a largely Chinese supply chain. Nuclear power technology can be exported for billions to countries like Pakistan, though China faces competition from Rosatom internationally. The solar photovoltaics industry reportedly employs 2.7 million people in China and is heavily reliant on the domestic coal industry for the refining of polysilicon. Meanwhile, a strong civil nuclear power industry translates into an up-to-date nuclear military capability. In China, the primary institution that develops civil nuclear power is also responsible for all its military applications. China's nuclear corporations. The Chinese nuclear industry is dominated by a handful of state-owned enterprises, similar to the Chinese defense industry. Headquartered in Beijing, China National Nuclear Corporation, CNNC, is the largest nuclear-focused state-owned enterprise and was originally the Ministry for Nuclear Industry. It is responsible for China's nuclear weapons program, but also for the production of uranium ores, fuel fabrication, fundamental research, reactor design, reprocessing, and waste disposal. It also operates 22 gigawatts worth of nuclear plants, or 41% of all nuclear capacity, often partnering with major electrical utility operators. A key subsidiary of CNNC is China Nuclear Engineering and Construction Corporation, CNECC. It is the primary builder of all nuclear power plants and is central to all construction. It was merged into CNNC in 2018. Headquartered in Shenzhen, China General Nuclear Power Group, CGM, previously called the China Guangdong Nuclear Power Group, originated in the southern province of Guangdong and is 50% owned by the Guangdong provincial government. Having only been established in 1994, CGN was historically the smaller player compared to CNNC, but since 2010 has financed new plant construction in China's economically dynamic south, while CNNC remains centered around northern plants. CGN now operates 54% of all Chinese nuclear capacity. State Power Investment Corporation, SPIC, was created in 2015 through the merger of the State Nuclear Power Technology Corporation and the China Power Investment Corporation. It is one of 5 large state-owned electrical utilities. Its profile in nuclear power is currently limited to owning 2.3 gigawatts, about 4% of capacity, at its plant in Haiyang, Shandong Province. It acts primarily as an investor in nuclear power and is expanding plans to finance new plants, both on its own and as a partner to CNNC and CGN, who remain the main reactor designers. The other major electrical companies, including China Energy Investment Corporation, CEIC, Datong, Huajian, and Huaning, are also financing additional nuclear projects. In the U.S., utilities are generally averse to building new nuclear plants due to their high capital costs and uncertain construction timeframes, as well as the inability to charge variable pricing for their power. While deregulation of the Chinese electricity market has been experimented with to accommodate intermittent renewables, the long-term dominance of state-owned enterprises makes financing nuclear power relatively easy. The nuclear industry and the larger electrical utilities all sit under the State-Owned Asset Supervision and Administration Commission of the State Council, SASAC, a body of the State Council, China's highest administrative government body. SASAC also ultimately runs China's defense industry. The National Development and Reform Commission, NDRC, and the National Energy Administration, NEA, with the approval of the State Council, approve plant proposals and set 5-year plans for wider energy strategy. Whereas the U.S. nuclear fleet is owned by a highly diversified set of utilities, companies, and investors, and the French and Russian fleets are all owned by a single state-owned enterprise, ownership of China's fleet is dispersed among a few state-owned enterprises that ultimately all report to the central government. China's model of creating many and often redundant state-owned enterprises was intended to foster competition in the 1990s, but in practice, this amounts to the same central government direction as in France or Russia, with the difference that the Chinese government supports nuclear expansion. As a result, nuclear expansion occurs despite high capital costs and long build times. For the energy security promises of nuclear power to pan out, a country needs a safe and reliable source of uranium. China has achieved a degree of self-sufficiency in the nuclear fuel cycle. It sources a third of uranium domestically, another third through joint ventures in mining operations abroad, and another third on the open market. There are 4 main Chinese enrichment facilities. The 2 largest were built with centrifuge technology from the Russian enriched uranium exporter Tenex, which is owned by Rosatom. One site was upgraded with domestically made centrifuges in 2013. Alongside this, Chinese reactors import enriched uranium from suppliers including Tenex and the British-German-Dutch nuclear fuel consortium Urenco. CNNC has also built 4 fuel fabrication facilities inland to fabricate enriched uranium into fuel. These are based inland in Sichuan and Inner Mongolia, perhaps as part of a strategy to move potential military infrastructure away from the coasts. It has also set up a fabrication venture in Kazakhstan with the Kazakh uranium producer Kazatomprom. For fabrication, it has used assistance from France's Framatome, the U.S. company Westinghouse, and Rosatom. Currently, some fabricated fuel is imported. CNNC is also building infrastructure designed to recycle spent fuel, but this is at an embryonic stage of development. While Chinese nuclear naval propulsion remains behind that of the US or Russia, this capability is likely to mature by the end of the decade. Chinese naval nuclear propulsion efforts began in 1958. As of now, the Chinese Navy has 6 ballistic missile submarines and 6 attack submarines utilizing nuclear propulsion. China currently lacks any surface vessels with nuclear propulsion. China's 2 aircraft carriers are not nuclear-powered. Since 2018, 2 conventional Chinese icebreakers have been built, and both CGN and CNNC have made announcements regarding the building of a nuclear icebreaker. The proposed vessel, the Shuilong 3, would be comparable in size to the latest Russian project 22220 icebreakers, and would make China only the second nation after Russia to operate nuclear icebreakers. The project, announced in 2019, has been limited in details, indicating initial difficulties. But being able to construct a nuclear propulsion system for a 30,000-ton icebreaker would enable nuclear propulsion for ocean-going military vessels, such as aircraft carriers. China builds Western designs better. Chinese reactor technology has relied heavily on reactor designs from other countries, particularly from France, the US, Russia, and Canada. About 59% of installed capacity is based on reactors either designed directly by French company Framatome or based heavily on French designs. Initially, these sites were reliant on French engineers to operate, and as Chinese engineers gradually became more proficient, French engineers became advisors or ended their services. Currently, 22% of capacity is built on Chinese reactor designs. CNNC and CGN had reactor designs based on the M300 and 10 pressurized water reactor, PWR, developed by Framatome. This in turn traces its design back to the U.S. reactor manufacturer Westinghouse. The Taishan plant is composed of 4 reactors using the European Pressurized Reactor (EPR) design, developed and owned by the French state-owned electrical utility Électricité de France (EDF), which owns a stake in the plant. Due to delays and design flaws, only 2 EPRs have so far been built, both of them by China. While the primary partner for China's nuclear industry was historically France, its stakeholders have pursued deals with other nuclear exporters with varied designs. For example, there are 4 Russian water-water energetic reactors, WWERs, at the Tianwan plant. This plant is owned by the Jiangsu Nuclear Power Corporation, which is co-owned by CNNC and the export subsidiary of Rosatom. The Qinshan plant has 2 Canada deuterium-uranium CANDU reactors based on designs from the Canadian Crown Corporation Atomic Energy of Canada Limited, AECL. Another design exported to China was Westinghouse's AP1000. It was manufactured domestically by China First Heavy Industries in 2014, and there are currently 4 AP1000 reactors. In 2022, a further 4 AP1000 reactors were greenlit. While China has been heavily reliant on foreign designs, it has proved a better environment to build those designs than the countries of their origin. Though these imports appear uncoordinated, they are arguably less about the reactors themselves than the associated expertise that comes with them. Partnering with Rosatom gives access to enrichment, fabrication, and weapons expertise. CANDU reactors, due to their unique design, can produce tritium, a key input for nuclear weapons or for any fusion-related research. Purchasing reactors from financially troubled companies like Westinghouse can be worth it if they are willing to sell the intellectual property as well, making future domestic development easier. This seems to be what is now happening. The AP1000 has struggled commercially, and so its deployment in China was likely heavily motivated by technology transfer. In 2020, State Power Investment Corporation released a domestic design based on the AP1000 called the Guohe 1. In 2011, meanwhile, CNNC and CGN combined their independent designs into the Hualong 1 reactor, managed under a joint venture. Both were developed through technology transfer, are built on established technology, and should be relatively simple to construct without marked delays. The Hualong 1 and Guohe 1 represent the vast majority of new capacity that is expected to be brought online in China up to 2035. The first Hualong 1 reactors began construction in 2015 and became operational in 2021, while the first Guohe 1 is expected to be operational at Shidaowan in Shandong Province by 2024. While the design is tied to certain companies, there is a high degree of collaboration between CNNC, CGN, SPIC, and the other major electricity utilities in sharing the fundamental design. Chinese research has also expanded to novel classes of reactors marketed as fourth-generation reactors. These include high-temperature gas-cooled (HTGR), pebble-bed reactors, sodium-cooled fast reactors (SFR), and molten salt reactors. From 2012 to 2022, alongside Huaning and Tsinghua University's Institute of Nuclear and New Energy Technology, CNNC developed the High-Temperature Reactor Pebble-Bed Module (HTR-PDM), a small modular reactor in the Shidaowan site in Shandong Province. It was the first ever fourth-generation reactor to be deployed for commercial use worldwide. This is a small reactor with only 200 megawatts of capacity, but there are plans to add a further 18 modules. Another SMR project is the Linglong 1, which was the first SMR design to be approved by the International Atomic Energy Authority. It is the first onshore SMR to be under construction, having begun in 2021. Rosatom has deployed floating SNRs in the Arctic region. The difference between so-called fourth-generation reactors and current reactors is that they use novel coolant methods. While most reactors today use light or heavy water as a coolant to control the fission reaction, novel approaches use sodium, gas, lead, or supercritical water as coolants. Depending on the coolant, these designs offer potential benefits relating to efficiency, being able to retrieve and recycle fuel, or making nuclear proliferation harder. The replacement of uranium with thorium as a fuel is another proposal outlined by fourth-generation advocates. The relative advantages of fourth-generation reactors versus established reactor technology are not revolutionary. There is no indication of massive economic improvements or a great increase in power density. While China is well placed to be the primary innovator in fourth-generation reactors, given the stagnating nuclear industries of other countries, it already has the technology it needs to rapidly expand production and exports. Also, since the primary drivers of the nuclear industry are state-owned enterprises, and the government isn't specifically planning to keep up energy consumption growth, this seems to be an opportunity that won't be seized without the intervention of a live player. The Chinese state-owned enterprises are capable of organizing vast expansions of nuclear power, but much like China's defense enterprises, are unlikely to see live players rise up the ranks and are therefore unlikely to innovate commercially. European traditions of knowledge have been acquired through technology transfer, but also from acquiring companies. The HTR technology demonstrator was based on the experimental German AVR reactor that ran from 1967 to 1988. The HTR program was reliant on consulting German nuclear engineers, as well as Chinese engineers studying at the Jülich Research Institute, where the AVR operated. In 2013, a little-known Chinese private company called Yantai Taihai Group became a shareholder in the French company Menor Industries, one of whose divisions specializes in civil nuclear power. This gave it access to piping, valves, pump bodies, impellers, and other components where nuclear safety demands high standards. In 2017, It bought the financially troubled German zirconium tube manufacturer Duisburg Tubes Production. In 2018, the German government blocked the acquisition of the machine tool maker Leifold Metal Spinning, a provider of cast and forged parts for civil nuclear equipment, by Yantai Taihai Group. China has effectively adopted Western designs and gained the necessary intellectual property to develop its own reactors that are of sufficient quality. The ability of Chinese companies to build fast and draw on considerable government support has also allowed the industry to achieve firsts in small modular reactors and fourth-generation reactors. The U.S. government will complicate Chinese nuclear exports. U.S. companies, in particular Westinghouse, rely on the growing Chinese market for potential sales growth. As recently as 2022, Westinghouse earmarked 4 additional AP1000 reactors to be built in China, bringing the total tally to 4. Despite this, the U.S. government has since 2018 restricted Chinese nuclear firms from doing business with U.S. companies. In 2018, CGN was banned from doing business with U.S. companies and placed on the Commerce Department's entity list, much like Chinese telecom giant Huawei. There has been a reduction in cooperation between the U.S. and Chinese nuclear industries. The U.S. nuclear startup TerraPower, funded largely by Bill Gates, partnered with CNNC in 2013. TerraPower's technology concerns the traveling wave reactor concept, which can run on depleted uranium, hypothetically ending the need for enrichment or fabrication and thereby lowering proliferation concerns. In 2018, U.S. export restrictions made such a venture untenable, and in 2019, CNNC exited the project. As of 2022, the Japan Atomic Energy Agency and Mitsubishi Heavy Industries have become TerraPower's new partners. U.S. restrictions have negatively impacted the immediate export potential of Chinese reactors. In 2020, Romania's government canceled a deal with CGN, instead deciding to partner with Western firms. For this, the Romanian government received $3 billion from the U.S. Export-Import Bank. In the United Kingdom, Chinese nuclear interests have also been curtailed. In 2022, CGN was forced out of its joint venture with the Sizewell C nuclear plant, in which it held a 20% share. CGN's ousting from the project contributed to a series of delays, putting the project's eventual construction in doubt. CGN continues to own a 33% stake in the British Hinkley Point C power plant, but is likely to contribute no further funding as cost overruns continue to build up. CGN's involvement in the British nuclear industry was only formalized in 2015, so it is effectively being forced out, highlighting how risky ventures with U.S. allies could be. It shows that foreign governments will oppose Chinese involvement for political reasons, even if they are having severe difficulty funding large-scale investments. Chinese reactors were initially considered for new nuclear plants in the Czech Republic, but in 2021 it was made clear they would not be considered. A Chinese ouster directly opens up opportunities for U.S. nuclear exports. With the U.S. market a non-starter and exports to U.S.-aligned countries in the developed world highly uncertain, Chinese nuclear exports will rather depend on more independent middle powers and the developing world, where China faces very stiff competition from Rosatom, the largest nuclear reactor exporter. The first major Chinese attempt at export of nuclear reactors was a 2015 deal to build a Wolong 1 reactor in Pakistan, one of China's key regional allies. The first unit became operational in 2021, while the second unit entered service in 2022. The successful export of a large reactor had previously only been completed by U.S., Russian, and French suppliers. In 2022, CNNC agreed to an $8 billion deal with Argentina to export the Wolong 1, with CNNC providing 85% of the financing. This funding comes with demands that fuel be imported from Chinese suppliers. CGM and CNNC have pushed for exports elsewhere, reaching memoranda of understanding with energy providers in Brazil, Cambodia, and Uganda. They have been encouraged by government plans to promote Chinese technical standards overseas. But so far, the Pakistan and Argentina deals are the only plants under construction. Due to the lack of local technical expertise, Chinese exports to developing countries will likely have to be comprehensive, with Chinese companies building, owning, and operating plants. Currently, Chinese companies are not as favored as Rosatom, but their spending power could be sufficient to effectively pay over the odds for exports. At present, exports are set to be nothing more than a supplementary business for the Chinese nuclear industry, as the US and US-aligned governments have effectively restricted access to established nuclear power markets, and the primary market by far remains China itself. China's nuclear expansion is unique but not revolutionary. China is anticipating an unprecedentedly large-scale buildup of nuclear capacity. With up to 250 gigawatts of additional capacity to be built in the next 30 years, China's nuclear plans will completely alter the character of the global nuclear industry. Currently, there are 413 gigawatts of nuclear capacity globally. By 2050, estimates range from this increasing to anywhere between 555 gigawatts to over 800 gigawatts. Assuming Chinese estimates of reaching 328 gigawatts by 2050 are realistic, between 40% and 60% of capacity worldwide would be Chinese. But while the global nuclear industry's future is increasingly likely to become more Chinese, China's energy grid will not be majority nuclear. Nuclear power remains capital-intensive and subject to delays, and for reasons both economic and political, there is significant support for the expansion of other energy sources as well. Coal is cheap and holds down Chinese electricity costs, cementing it as the primary manufacturing superpower. Wind turbines and photovoltaics are increasingly built on Chinese supply chains. They have advantages in securing energy, but also act as excellent job creators, demanding enormous investment in refining, sourcing materials, and building additional transmission infrastructure. Natural gas is a necessary complement to intermittent renewables. Compared to these, nuclear has a clear role, providing stable baseload energy, improving energy security, and developing expertise for military uses. However, the ultimate potential of nuclear fission, and more speculatively nuclear fusion, is to provide energy abundance on a scale beyond which any developed country has obtained. Such an expansion in available energy would be a necessary prerequisite for transformative technological change or economic growth on a societal or even civilizational scale, such as for large-scale replacement of human labor through automation. Under current Chinese plans, this potential will continue to go unfulfilled. Chinese elites are planning to become a developed country where energy consumption growth eventually stagnates and the focus of energy infrastructure becomes efficiency rather than continued growth. If this occurs and China follows the Western trajectory, then the potential for transformative technological change in the global future will be greatly diminished, since the only other plausible candidate to effect such a nuclear expansion the United States is not planning to. But whereas Western plans and institutions are in large part guided by anti-nuclear ideology, there is no equivalent anti-nuclear faction in the Chinese elite. Whereas new nuclear construction has effectively stopped in the West, China is expecting to more than double its own nuclear capacity. The potential remains for live players in China's government and nuclear industry to greatly adjust plans for nuclear expansion upwards. Should they choose to do so, there would not likely be any major obstacles in terms of expertise or materials, and Chinese civilization would for the first time in centuries have a realistic shot at surpassing, not just catching up to, Western societies.